There's a moment, captured on video, studied by engineers and shared by nervous passengers, where a Boeing 787 Dreamliner's wingtips flex upward during takeoff. Not an inch, not 2, 12 feet. And the first time most people see it, they think the same thing. That's not supposed to happen. Here's what's strange. They're wrong. Every centimetre of that flex was calculated, tested, demanded by the engineers who designed this aircraft. But here's the question that nobody was asking in the right way. Why would you want your wings to bend like that? What does it achieve that rigid wings can't? And what happens when the material doing the bending is something aviation had never used at this scale before? Because the 787's wings aren't aluminum. They were never going to be aluminum. They're woven, and carbon fibre, laid down in precise orientations, layer by layer, cured in an autoclave the size of a building, composites, unlike anything that had carried passengers before. Not just in quantity, in structural philosophy. This is the story of why Boeing made that choice. What it took to prove those wings were safe. The moment during testing when the math said one thing and the metal, the composite, seemed to say another. And the question that still divides aerospace engineers today: when you build something designed to flex, how do you know exactly where flex ends and failure begins? To understand why the 787's wings work the way they do, you have to go back to a problem that aviation had been accumulating for 50 years: weight. Every generation of commercial aircraft got heavier, engines got more powerful to compensate, more fuel was burned, more fuel meant more weight meant stronger structure meant heavier airframe, and the cycle reinforced itself in a way that made every efficiency gain a negotiation against physics. By the early 2000s, Boeing's engineers understood something clearly. Aluminum had given them most of what it could give. Not that aluminum is a bad material. For decades it was extraordinary. Lightweight relative to steel, machinable, well understood. The entire body of knowledge about aircraft fatigue, about how cracks propagate in metal, or about inspection intervals and repair procedures, it was built around aluminum. It was a solved problem, mostly. But aluminum has a ceiling, and Boeing was approaching it. At the same time, Airbus was building the A380, the largest passenger aircraft ever constructed. A bet on hub-to-hub travel, giant airports, maximum capacity. Boeing looked at that strategy and made a different call. They weren't going to build a bigger plane, they were going to build a more efficient plane. Smaller, longer range, point-to-point routes that didn't need hubs. An aircraft that could open city pairs that wide-body jets had never been able to serve economically. That aircraft was the 787. Later the 787, and from the beginning, the efficiency targets were ambitious enough that conventional construction wasn't going to get them there. And they needed roughly 20% better fuel efficiency than comparable aircraft. To get that, they needed to save weight, dramatically, and they needed better aerodynamics. Both answers pointed the same direction. Carbon fibre reinforced polymer, CFRP. Composite material, not new to aviation. Military aircraft had used it. Business jets used it in control surfaces, in fairings. But nobody had built a commercial wide-body fuselage from it. Nobody had built wings at this scale from it. Boeing committed. 50% of the 787's structure by weight would be composite material. Here's what the brochures said. Composites are stronger than aluminum, lighter than aluminum, and don't corrode. All of that is true. But there was a fact buried in the engineering literature that the public rollout didn't lead with. Composites don't behave like metal. A metal bends before it breaks. It gives you a warning. You can see a crack. You can measure its growth. You can predict its behavior from decades of accumulated data. Composites do something different. They can carry extraordinary load right up until they can't, and then they fail suddenly in ways that can be hard to detect and harder to predict. That's not a flaw, that's a characteristic. And Boeing's engineers knew it. The question was whether they could design the 787's wings to exploit the advantages of composite material while engineering around its most significant challenge. The answer required rethinking what a wing was actually for. Let's talk about what a wing actually does structurally, because most people have an incomplete picture. The intuition is, wing holds the plane up. True. But that's the aerodynamic job. The structural job is more specific and more violent. When a plane generates lift, the wings want to bend upward. The air pressure under the wing is pushing up. The weight of the fuselage, the engines, the fuel, the passengers, is pulling down. The wing is caught between those forces. It flexes. Every wing flexes, always has. The question is, how much and what material absorbs that flex most efficiently? In an aluminum wing, you control flex by adding structure. Spars, the main load-bearing beams running spanwise through the wing, ribs running chordwise, skin panels riveted to the skeleton beneath. The system distributes load across a rigid framework. Rigid is good. Rigid is predictable. Rigid is also heavy. Here's what Boeing's composite engineers understood about carbon fiber that changed the equation. You can tune it. Carbon fiber isn't one material in the way aluminum is one material. It's layers, plies, each oriented at a specific angle. 0 degrees plus or minus 45, 90 degrees. The orientation of each ply determines how that layer responds to load. Change the layup sequence, and you change how the structure deforms under stress. This is called aeroelastic tailoring, and it's the reason the 787's wings flex the way they do. The design goal wasn't to minimize flex. The goal was to control what kind of flex the wing exhibited under different loads, and to make that flex work aerodynamically rather than fight it. Imagine a wing that, as it bends upward under load, also twists slightly, leading edge up, trailing edge down. That twist changes the angle of attack across the span. Done correctly, it can actually improve the lift distribution during high-load maneuvers. The wing becomes more efficient precisely when it's being worked hardest. That's not an accident. That's the fiber orientation doing exactly what the engineers programmed it to do. But here's where it gets complicated. Boeing didn't build the 787's wings. Not entirely. They designed them. The manufacturing was outsourced to Mitsubishi Heavy Industries in Japan, who built the wing boxes, to other suppliers across the supply chain. The integration model was new, the component complexity was new, and the testing program that had to validate all of it was unlike anything Boeing had run before. And the FAA requires that a commercial aircraft wing must be able to withstand 1.5 times the maximum load it will ever encounter in service without failing. Called the limit load and the ultimate load. And not just theoretically, you have to prove it in a static test. You take a real wing, you load it to destruction, you have to reach 150% of maximum designed load before failure. For the 787, that test was conducted at Boeing's facility in Everett, and the results were watched by engineers who had, by that point, spent years running simulations and building confidence in their composite model. The wing was loaded. Hydraulic actuators pushing up on the span at multiple points, simulating the aerodynamic lift distribution. Instrumentation throughout, strain gauges, deflection sensors, feeding data in real time. I'm at 100% of limit load, nominal maximum operating load. The wingtip had deflected approximately 25 feet from its resting position. The wing continued to load. 110%, 120%, 130%. The engineers watching had numbers to compare against. The composite analysis had predicted specific failure modes, specific load levels, specific locations where damage would initiate. At approximately 150%, they got what they needed. The wing passed. But there's a detail in how composites fail that matters here. When that 787 wing ultimately reached its structural limit, It didn't bend and permanently deform the way a metal wing would. The failure mode was different, rapid, sudden, which brings us to the hardest problem in composite aircraft design. How do you inspect a wing you can't see inside? With aluminum, fatigue cracks start small and grow slowly. Inspection intervals are calibrated to catch them. You can see the surface. You can use eddy current testing to find subsurface cracks. The entire airworthiness system for metal aircraft is built around the visibility and progression of damage. Composites can have internal damage, delamination between plies from impact or manufacturing defect or cyclic fatigue that's invisible from the surface. The wing looks fine. The outer ply is intact, and inside the structure is compromised. This is called barely visible impact damage, BVID. It's not hypothetical. When composite aircraft components are struck, by hail, by ground equipment, by debris, the energy can propagate internally without leaving an obvious surface mark, and unlike a metal crack, delamination doesn't announce itself. Boeing knew this, the FAA knew this, and the certification program for the 787 had to address it directly. And the answer they developed shaped not just the 787, but the entire framework for how composite commercial aircraft get certified going forward. The approach was threefold. First, design the structure to tolerate damage, not just withstand it, tolerate it. The composite layup in critical areas had to be able to carry load even with internal delamination present. This meant redundancy built into the fibre architecture itself. If one ply group was compromised, adjacent plies maintained structural integrity. The wing had to be fail-safe not just systemically but materially. Second, establish inspection methods that could find internal damage reliably. Ultrasonic testing, sending sound waves through the structure and analysing what comes back, can detect delamination that's invisible to the eye. Thermography, shearography. The 787 maintenance program includes composite-specific inspection procedures that are fundamentally different from metal inspection. Third, test the assumptions relentlessly, not just the wing in isolation, the material. Boeing built panels, coupons, subcomponents representing every major structural element, subjected them to fatigue cycles, to impact, to temperature extremes, to moisture absorption. Composites absorb moisture over time, and water changes their mechanical properties. The test articles had to demonstrate that the real-world operating environment didn't degrade the material below certified limits across the aircraft's designed service life. And that testing program took years, and it still produced surprises. One area of genuine difficulty: the interface between composite structure and titanium fasteners. The 787 uses titanium hardware extensively in its composite structure. Aluminum creates galvanic corrosion problems with carbon fibre, so titanium replaced it throughout. The behaviour of fasteners in composite joints under fatigue loading was less well understood than the equivalent aluminum behaviour. It required analysis that, in some cases, pushed the boundaries of existing models. There were also manufacturing quality issues during the early production period, not unique to Boeing, but significant. Some barrel sections of the fuselage had composite shims installed to fill gaps rather than the sections being remade to tolerance. Or the FAA required Boeing to demonstrate that the shimmed structure met certification requirements. They did. But it was a signal of the challenge in transitioning an entirely new manufacturing approach to production scale. The 787 entered service in 2011. Late, 3 years behind the original schedule, a delay that cost Boeing billions and burned through its relationships with airline customers. The technical ambition had collided with the reality of developing an entirely new manufacturing ecosystem simultaneously. But the wings worked. They bent exactly as calculated. They twisted as the fibre orientations dictated. And over more than a decade of service, on routes from Tokyo to London to São Paulo, the composite wing has proven what the engineers had argued in those early design reviews. You don't have to make it rigid to make it safe. You have to make it right. Here's what the 787's wing actually represents, and why it matters beyond this one aircraft. Aviation had always advanced by solving the problem in front of it. Fatigue cracking in metal, better inspection programs, corrosion, better surface treatments, weight, more powerful engines. The 787 was different. It didn't solve a problem that existed. It chose a harder problem in order to access a larger solution. The engineers who designed that wing could have built it in aluminum, and the 787 would still have flown. It would have been heavier, it would have been less efficient, but it would have used understood materials and understood manufacturing and understood certification pathways. They chose composites because the prize, 20% better fuel efficiency, 30% lower maintenance costs, the ability to pressurize the cabin to 6,000 feet instead of 8,000 for passenger comfort was worth the difficulty of building something genuinely new. And the difficulty was real. Ask the airlines who waited years past promised delivery dates. Ask Boeing's shareholders who watched the program bleed money. Ask the engineers who spent careers learning to think in fiber orientations and failure modes that had no handbook when they started. But ask a passenger on a 787 about the flight. The lower cabin altitude is measurable. People arrive less fatigued on long-haul routes. The larger windows, possible because composite structure carries load differently than aluminum frames, change the experience of flight. These aren't marketing claims, they're engineering consequences. The flex you see in that takeoff video, it's not an anomaly. It's not a flaw. It's the wing doing exactly what it was designed to do, distributing load across a material that's simultaneously stiffer and more flexible than what came before, in the directions that matter, in the ways that make the aircraft more efficient with every flight cycle. Every time a 787 takes off, that wing is running a calculation. Thousands of carbon fiber plies, each oriented with intention, each carrying its share of the load, the whole system bending and twisting in the precise pattern that Boeing's engineers specified 20 years ago. It works because they understood the material well enough to make it perform, not just survive. The question that remains. But here's where the story doesn't fully close. We know composite wings can be certified. We know they perform as designed. What we're still accumulating is the long-term data. The 787 has been flying for just over a decade. Metal aircraft have given us 70 years of fatigue data. We know how aluminum ages because we've watched it age. Composites are younger in service. The inspection programs are rigorous. The analysis is sophisticated. But the empirical record, what actually happens to carbon fiber wing structure after 30,000 cycles, after 25 years of airline operation in the full range of environments a global fleet encounters, that data is still being written. The engineers who certified the 787 made sound decisions based on the best available analysis. The aircraft has an excellent safety record. But humility requires acknowledging that we are still learning, and that's not unique to composites. Every generation of aircraft technology is partly a bet on predictions. Metal wings cracked in ways early designers didn't anticipate. Composites may reveal characteristics over decades that the models don't fully capture. The question isn't whether the 787's wing design was right. The evidence says it was. The question is whether the industry's ability to understand and inspect composite structure will keep pace with the fleet as it ages, and whether the regulatory frameworks built around metal fatigue thinking have fully adapted to a world where the dominant structural material behaves in fundamentally different ways. We know what the wing does. The deeper question, do we know everything it will do? Aviation has always answered that question the same way. By flying, by inspecting, by learning. By building the knowledge base that the next generation of engineers will use to design wings we haven't imagined yet.